it becomes 1. So, which means for this one, so now the order kind of changes. Since we are for floating point numbers, instead of taking them down going up, we take it up going down. So this one would be 0.01 in binary. That would be the value in binary. Let me just use 3 to represent the binary value. So now this begs the question, since our problem comes from this 0.1 f, the floating point for 0.1, I wonder what our 0.1 should be. So if we do it manually, we'll have 0.2, and 0.2 times 2, 4, 0.4 times 2, we have 0.8, 0.8 times 2, we have 1.6, and then in this case, since we're taking this value, we just remain with the decimal value. So we have 0.6 times 2 equals 1.2. So now we go back to 0.2 times 2, 0.4, 0.4 times 2 equals 0.8. I don't know if you are back with us, James.
Yeah, I'm back.
Oh, nice. So I don't know what's going on here. We've started repeating our values.
Yeah.
I don't know if you've noticed that.
Yeah.
So we started getting 0.2, and now we're repeating. So if you continue here, it will just continue being 0.000110011, and so on and so forth. So just a repeating sequence here.
Yeah.
So I'm guessing this is where the issue comes in.
Yeah.
I would like to believe so.
It will make sense as well.
I don't know. Yeah.
As to based on that calculation that you just did, since it's a recurring number over and over again, that means at some point the machine kind of truncates it to something like that. I think. I'm not sure. I'm assuming.
Yes. Yeah, probably. So let me see. I'm just curious to see whether whatever we've calculated here is what the machine, if we put it in code, if you request to see, so just going here how to convert. So just copy this as is. Let me just replace that. So since we're looking at 0.1, I'll just do that, and then it's set. Okay, so this is doing here where we are converting this float that we have here, 0.1, into the binary value that is now stored in our machine.
Okay.
So if I take a look at the value, let's see what it will print out. This is interesting. Look at this. This is not the same value as even for starters. It's starting with 1.
Okay.
Just zoom it so that everyone can see. Zoomed a bit too much. Look at this. So ours is starting with 1, and this one is starting with. Ours is starting with 0. This one is starting with 1, which yeah, that doesn't make any sense.
Yeah, it doesn't.
But I'm actually noticing there's this. Okay, there's a bit of familiarity. If you can look at this, there's this 11, let me just call it 11 0 0 11.
Mm-hmm.
It's kind of repeating here.
Yeah.
So maybe it's the same. I don't know.
Mm-hmm.
Maybe, okay, I don't know. Maybe the machine saw it in a different way.
Mm-hmm.
So let me go back to this first site. Let's see. So for floating point numbers, so according to this site, root.hashnode.dev, so they're saying there's a certain way
Mm-hmm.
that floating point numbers are stored,
Mm-hmm.
and it's not the way we calculate it per se.
Yeah.
So so they're saying assign an exponent, mantissa. That's a lot of jargon, but maybe we can go to this example. So a single bit that represents the sign of the number.
Mm-hmm.
Okay. So having read this a little bit, so a bit of an explanation. So it seems that we are okay. The first bit,
Mm-hmm.
this one,
Mm-hmm.
the first bit will represent whether it's positive or negative,
Uh,
which would make sense because if we just have a number, we don't know whether it's positive or negative.
yeah, yeah,
So
yeah, yeah.
the first bit,
Mm-hmm.
whether it's positive or negative, so 0 for negative, 1 for positive,
Mm-hmm.
and then we have an exponent. So an exponent is a fixed number of bits that represents the magnitude of the number,
Mm-hmm.
typically in scientific notation.
Mm-hmm.
So I think we know the exponent for like the normal type of exponent. So for example, if it's this 0.25,
Mm-hmm.
usually we put it like 2.5 times 10 to the power of is it
What?
-1, right?
Mm-hmm. Yeah.
Yeah, to the power of -1. So this is a decimal. This is decimal representation.
Yeah.
So for binary representation, so if I take this for example and we try to do it in to do an exponent for it,
Mm-hmm.
we'll get 1.10011. This is a point. So we've moved the decimal place from here. Let me just represent it correctly. So we've moved it 1, 2, 3, 4 times.
Four times.
So this will be time two. Since our base we are in binary, so our base will be two, not 10.
Mm-hmm.
Power of 4. And
Mm-hmm.
then you notice for this one, even though we're moving this direction,
Mm-hmm.
it will this will still be positive,
Mm-hmm.
not a negative like in the decimal, because it's kind of like we have inverted it. So the same way that when we're calculating the binary for a whole number, we are dividing. When we're calculating for for a float number, we are multiplying. And
Mm-hmm.
then when you're picking the values, you're picking from for decimal, we're picking sorry for whole number, we're picking from bottom to top, and then for this, we're picking for decimal. I mean for floating
Float.
point
Yeah.
numbers, you're picking yeah, top to bottom.
Mm-hmm.
So now this will be the way it will be represented as an exponent. But
Yeah.
then there's something here that is I had read it before that they usually add a bias. So a bias. So I don't know if you know this, but our the floating point numbers are usually 32 bits.
Okay.
Stored in memory is 32 bits.
Mm-hmm.
Yeah. So the bias for a 32 bit will be 127.
Mm-hmm.
This is 2 to the power of 8
Mm-hmm.
minus 1.
Why?
So 8 32 bits. That's because 32 bits is 8 bytes.
Yeah.
So 8 bytes So 2 to the power of 8 minus 1. So that's how they calculate the bias. So now this bias 127, they add it to, so our exponent in this case will be this 4, right? So whatever is stored in memory is now 127 plus 4. So this is something interesting, because at the first time when I saw this, I was wondering, what is that bias for? I mean, why do you need to add 127 plus 4? But then I read an explanation that said it will allow us to know whether it's positive or negative.
Okay.
So if this exponent is positive, then our value will be above 127. If it's negative, then it will be below 127. And whatever value we get will still be within the range of those 32 bits. So that's how it's stored. So so coming back here, so that will be our next is it 8 bits? Let me see. So now that one, let me just use a site here to convert. So for hours, 32, 127 plus 4 will be 131.
Yeah.
Right?
Yes.
So let's see what 131. I'll just use a calculator. From decimal to binary, we're converting 131. Convert. So it's this. 0, 0. Oh, this. Wait a second. It's not adding up.
Up to like based on
This one?
based on what I was looking at before, I could say like it was matching. We'll go back to your term, yeah, and also your notepad.
On my notepad. You
If
just put them all so we can see.
yeah, if you look at what you have selected on the notepad, as well as you look at the output that you have on on the terminal, up to their matching is just that doesn't have the decimal point.
Yeah, that's true. The first bit.
Yeah, so and then you said, remember you said that after that point the number now keeps repeating itself.
Yes.
I the only place now that actually it does it now it goes back trying to recreate that thing over and over again. Now this one even becomes more confusing.
Yeah. So okay, the part that I see is repeating. Let's see. Supposed to start with 110 01100110011. Maybe they add something extra, but I'm expecting that we should also have this value somewhere.
That one I can't see.
Or maybe is it that they add, because I'm also seeing this. I don't know if let me increase the size of this one.
Yeah, you can see it.
Because I'm also seeing this value here.
Yeah. 1, 2, 3, 4, 5. No, it's not that.
Those
That
are
has
5. This is 4.
Yeah, that's 4.
No, it's not. Interesting. So the exponent determines. Okay, maybe it's because let's see if we finish this, we can get exponent determines the scale of the number, indicating whether the decimal point should be placed. Mantissa, also known as a significant fraction, this component represents the significant digits. So the mantissa is a variable length sequence of bits that contains the digits of the number. Okay, the mantissa is basically what we originally had. guess this is. Huh, I would like to see the actual calculation. An example with an actual calculation so that because now at least we have an explanation, but the number we are seeing here is not what we're expecting.
Yeah.
At least we know the first one is a bit. Let's see. So how computers store? It's about how they store the floating point numbers. Oh, this looks. Oh, nope. uh, okay, let's see this one. Excuse that. Okay. I guess this is the standard for IEEE 754 standard is what is used. Yeah, so the sign bit. Okay, so here's a bit of a visual explanation. So we have the first bit is a sign bit. I think we already understood how that comes about.
Yeah.
Yeah. Then we have the exponent, which is the next 8 bits. Okay. So we have the exponent. So 1, 2, 3, 4, 5, 6, 7, 8.
Mm-hmm.
Let me
Yes.
just copy this and see what its value is. So from binary to decimal,
Mm-hmm.
let's take this and convert. 155.
How did they get to 155?
Yeah, that's a question. Because now we're expecting it to be. Huh. Let's see. Let's see if they can give an explanation. Hmm. Okay, so here's a bit of a visual explanation. I hope you can see what I'm saying.
Yeah. Yeah, I can see it properly.
Okay, so they're actually using our example. So for this, they have 9.1.
Mm-hmm.
So converting 9, I don't think that's a big hassle for us.
Mm-hmm.
Then converting 0.1 now,
Mm-hmm.
um, they have the same value we got here, not here, this.
It's bad. Uh-huh.
So we have 0.0001100, yeah, and then it's repeating.
Mm-hmm.
And then the fraction part,
Mm-hmm.
uh-huh. So this is the integral part, this is the fraction part. So this is what the number would look like basically.
Yeah. Yeah.
And then now let's write this in scientific notation as below. Oh, wait.
Scroll up a little
Even though
bit.
9,
What did they do? Trying to see. Okay.
yeah. So we've converted 9 already. So
Mm-hmm.
this is the value of 9,
Mm-hmm.
and this is the value of 0.1.
Yeah.
So it's nothing different from what we are used to.
Mm-hmm.
So this is the value of 9. This is the value of 0.1.
Yeah. Yeah.
Then here,
Mm-hmm.
even though 9.1 is an infinite binary number, we have only 23 bits to store it.
Okay.
Now let's write this in scientific notation as below. So for here, 9.1, so it is I believe this should be 2 power 3. The two exponent of 3, 2 as the base, and then, because it will make sense, so you see we have 3 here. So maybe the site didn't capture that
Okay. Okay.
incorrectly.
Mm-hmm.
So next, this number should be written in IE 754 format.
Mm-hmm.
So if the number is plus,
Mm-hmm.
the sign bit should be 0. Oh, if the number is positive, the sign bit should be 0. If the number is negative, the sign bit should be 1. Oh, I guess we got that wrong.
Yeah.
So according to our example, the sign bit should be 0.
Mm-hmm.
Yeah, so 0 represents positive and then 1 represents negative. That's good to know. Then here exponent is an 8-bit value. Since this is a single precision value, Therefore, bias is 127. Now, you should calculate the binary of bias plus exponent, as in here,
Mm-hmm.
127 plus 3.
Mm-hmm.
Yeah, exactly what you had done.
Mm-hmm. Mm-hmm.
And the binary
Yeah.
of 130 is this.
Yeah.
And this is our exponent bias. Oh,
Mm-hmm.
which adds up according to that. So we have this.
Mm-hmm.
Okay, oh, this is different because this is 9.1.
Yeah.
Oh, it will be different from what we have.
Mm.
Okay, okay. But that makes sense. And then I guess this is just them explaining what you've just done.
Mm-hmm.
And then now we have our mantissa, which is what is repeating here.
Yeah. Yeah.
Yeah, I think that makes sense. So we have our sign bit, we have our 8 bit telling us what exponent it is, and then we have our mantissa, which is basically what we've just conversion of floating point number into binary.
Yeah.
So the whole of this will be a 32 bits, uh, 32 bits.
Yeah.
So I guess it comes at the end of the day, we end up with it's a pretty okay. First of all, this standard format is kind of genius. I like it.
Mm-hmm.
However, it doesn't solve all the problems
Yeah.
when it comes to calculating. So we get this unexpected value.
Mm-hmm.
So, but if you use a computer floating point converter to calculate this representation, you'll see a change in
The last bit. I think I lost you for a minute there. Yeah, as we wait for Michael to come back, this seems, for me, this seems like um, a more issue pertaining how it is rounding off that the last those digits, especially when it comes to bit number, and then once that's done, converting it back to now, let me call it readable, human readable, it becomes even more confusing. I think Michael, you're back.
yeah, I'm back.
Yeah.
Just lost a bit of net there. Um, yeah, so that kind of breaks the mystery. So at least now we know how the computer stores it,
Mm-hmm.
and now we know where the problem comes in.
Yeah. Yeah.
And I guess this kind of answers why I don't know if you've encountered this, but usually when you're dealing with let's say systems that need precision,
Mm-hmm.
we usually use 64-bit uh, 64-bit values,
Mm.
or let's say floating point values with 64-bit. In C++, they're usually called long. I don't know.
Okay.
I've never tried to interact with them on.
On a higher language.
Sorry.
Yeah.
Yeah, I've never tried on higher level language.
Mm-hmm.
But I know if in a system such as let's say a game engine where those calculations are necessary when calculating let's say light or doing physics simulations, uh, they usually use 64-bit floating point floats.
Mm-hmm.
I'll just use that because the best I can say it. 64-bit floats to do the calculations because they will be more accurate. Since they are storing more bits,
Mm-hmm.
then the accuracy is a bit more. It will not be 100% since we
Yeah.
still have um, those floating points that will still have a recurring um, they call it a what? Mantissa, yes, a recurring mantissa.
Mm-hmm.
Though even with this, that begs the question because we still have to design systems. So if we're encountering an system where, let's say it's a bank system or a
Mm-hmm.
circle system, maybe you're dealing with people's money. Of course, it has to be accurate.
Yeah. Very.
So I wonder what can we do to to have it done correctly, such that no such errors, even to the smallest degree, can happen.
Yeah.
Even adding a cent can bring a huge problem in the future.
Yeah. Uh,
And it's a,
yeah. Before I answer that, hi Rahul. Thank you for joining the stream. So the what you're discussing on here is it's more of a math error in terms of when you're doing sum with programming. That is, if you've ever done any calculations in any programming language, especially when you're dealing with currency or money, you end up finding that there's usually some sort of rounding errors, especially if you're doing, let's say, 1 plus 0 0.1 plus 0.2. Let me show you an example. If you're doing this, you'll always find that the output will be something weird to the end. So if you're adding several amounts, you'll end up finding that that amount is not adding up. So either you'll be stealing from your client, or the client will be stealing from you, one of the other way around. So we are trying to establish where the actual problem is coming from. And then at the end of it, we are now at the point where we are trying to find the actual solution to this problem. So now to explain how to solve this problem is, especially if you're dealing with currency, this is the perfect way to deal with it. So remember, based on our conversation, the problem is coming at the point where we're dealing with floating points. So it's at this point we're adding point 1 or point 2 or any other floating point. That's where the actual error is coming. So to solve this problem, what I'll generally do is uh, I'll declare a is equals to, for example, 0.1, and then that number I'll convert it to a whole number. That makes sense. By that,
yeah, yeah.
what will happen is this number will now become it will become a whole number, and then from there we can be able to do our calculations as an integer, and then once we are done, we can always reconvert it back uh, to the float if you need to present it somewhere. If you've ever worked in any payment gateway, if you're a very serious payment gateway, you realize that all the time they're always asking for you to send the amount in cents, and that is the same thing that is the same thing that you'll always find uh, we need to actually do. So if I do, let me just do that, and then b is equals to 0.2 times 100, and then on here, if I do a plus b now, you'll see that we get now 30. But if I save this, well, c is equals to a times b, and then this c I convert it back to the floating point, we'll actually find the perfect answer. Hope that makes sense. This is
Yeah, that makes sense.
sorry, go on.
I think especially for currency. Sorry. Oh, sorry. Yeah. So I think especially since for currency we usually have only two decimal points. Yeah. Like which will basically represent, okay, for now Kenya will be shillings. If it's best, it's and
Yeah,
I
yeah.
believe that their sense.
Mhm.
But yeah, so it's usually two decimal points. So this really works well for currency when you're dealing with currency.
Yeah, yeah. So maybe whatever we implemented, this is across all the programming language that you'll use, and this is how you end up solving that problem. So if you ever encountered, or if you're dealing with money, please always remember to convert it into cents. It's rather you store that, always store your amount in cents in terms of whole numbers, and then at the point where you're displaying to your client, that can be your front end or your user or whoever is using your system, you can always convert it back to the float or your fixed amount. Because if you decide that you, for example, you'll use fixed and then you set the limit, how sure are you that the the output will always be accurate if that's what you're actually ending up to see? Hope that made sense to you guys. Just to maybe because I used that, I can do the same code in the other two languages, just for someone who can't understand what I just did. So for Python, I just create a is equals to that times 100, my bad, b is equals to, and then c is equals to that, then print c divided by 100. Then the output is the same now for JavaScript. And then b plus times
Nice.
c equals to a plus b. Then now you can be able to see the two difference. Now here we have the perfect answer, and here we have
Yeah.
the other error. Mm, I think that's all, unless Michael, you have anything else?
Nope. I think that's great. So I would say for high level languages, you just declare a constant or a variable. I would say if you can, it's usually good to cast
Mhm.
to implicitly cast. Like for example, when you're doing that multiply by 100, then convert that to an integer directly,
Mhm.
so that it's a guarantee that it will be an integer and um, not that floating point number that has those extra. It's usually a good proportion. That's one of the things that I recommend. Yeah.
Um, that's I think that's it. Thank you so much for joining us on this. Next time we'll be live on Wednesday from 9 to 9 Kenyan time. That is East African time. You can always join us, and we can always discuss new things or things that you actually could be ignoring, but they have huge implication if this code is pushed on production. So thank you so much for whoever joined, for everyone that joined, and you've been us from the start to the end.
Yeah. Thank you guys too. We'll see you next Wednesday.
Bye.